Okay, this question is about light. It's calculating the speed of light inside the ice cube. You've given some data here, and we've got our data booklet here for some equations. So we have to calculate the speed of light inside the ice cube. Now from topic 4.4 we've got n1, which is the refractive index, over n2 equals sine theta 2 over sine theta 1 equals v2 over v1. So we don't really need to calculate the refractive indices at this stage, but we do have angles and we do want to calculate velocities. Now if we call this 1 and this 2, then we've got sine theta 2, which is 33 degrees, sine 33, over sine theta 1, which is sine 46, equals the speed in 2, which is what we want to find out, over the speed in 1. Now 1 is just air, so the speed of vacuum, so the speed of light is c. So sine 33 over sine 46 multiplied by c gives us a v2 of 2.3 times 10 to the 8 meters per second. Okay, the second part of this question says that show that no light emerges from side AB, so that side there. So this ray of light is going to strike side AB and no light is going to emerge. So we can assume that total internal reflection is going to happen because no light is emerging. However, it's 3 marks, so we have to prove that numerically as well. So for total internal reflection to occur, we can find the critical angle by saying that the refractive index of the material, which we call 2 here, is 1 over sine c, where c is the critical angle. So n2 here is v1 over v2. So c over 2.3 times 10 to the 8 from this question up here gives us 1 over sine c. So sine c works out as giving you a critical angle of about 50 or 50.1 degrees. So then, okay, that's a little bit confusing because I've used the speed of light as c and also c is the critical angle. So here I'm going to change that to 3 times 10 to the 8. So here we've got our critical angle. Now what is our angle of incidence? Well, this light is going to continue up here, and so the angle of incidence, which is the angle from the normal to the ray, is going to be this angle here. Now from corresponding angles we know that that angle is 33 degrees, so this angle down here must be 57 degrees. So 57 degrees is greater than the critical angle, so total internal reflection happens. Finally, sketch on the diagram the subsequent path of the light ray. We've already kind of done that, but we're going to go in at an angle of 57. Total internal reflection is going to happen, so that angle of reflection is going to be 57 degrees as well. And then as it comes up to the glass block here, it's going to refract out again, so it's going to come like that. And remember to include the arrows for your light rays. Okay, so the next part of this question is about thermal physics. So we've got each side of the ice cube is 0.75 meters in length. So we've got a cube 0.75 by 0.75 by 0.75. So from that we can calculate the volume, and we have the density of the ice here, so we can calculate the mass. So density is mass over volume, and we want mass, so mass is density times volume, which gives us 920 times 0.75 cubed. And that gives us a mass of 388 kilograms. So now we're determining the energy required to melt all of the ice from -20 to water at a temperature of 0. So not only do we have to heat the ice from -20 to 0, we then have to melt it as well. So the total energy that we're putting in is going to be the amount of energy needed to heat up that ice. So we've got mc delta T plus the amount of energy needed to melt it, which is ml. So the energy is the mass, 388, times the specific heat capacity of the ice, which is 2.1. Now pay attention to your units here, times 10 to the 3 joules, times the temperature change, which is 20 degrees, plus 388 times the specific latent heat, again pay attention to your units, times 330 times 10 to the 3 joules. Okay, so that gives us a total energy of 1.4 times 10 to the 8 joules. Now, finally, you need to outline the difference between the molecular structure of a solid and a liquid. Anything that relates the structure of the solid to the liquid is acceptable here. So, for example, the nearest neighbour molecules cannot exchange places. The molecules have fixed positions. The molecules are closer to each other in a solid. The molecules have a regular pattern. They're arranged in a lattice formation. They have stronger forces of attraction. Any of those things. Conversely, you could say the opposite about any liquids, about the state of any liquids. So, for example, liquids do not have a regular pattern, or liquids are not in fixed positions. Or you could say something like, in a liquid, the bonds between molecules can be broken and reform. So any of those things gets you that 1 mark.